We in the last class we ended at word embeddings, and today we will finish this the course on sequence models, and we will then try to see some examples in TensorFlow. So there are basically two algorithms with which you can learn word embeddings. So one is known as word to vec, and which are popular. One is word to vec, and another is glove. So we finished here last time on how to basically create or how to learn word embeddings, and so when people started using word embeddings, they used to be complex, but they are getting simpler and simpler. With most of the applied researchers these days using pre-trained word embeddings, and in word embeddings, you would basically start by learning complex examples to make intuition. For example, in this neural language model, if you start with this example, I want a glass of orange. So, and what should be the last word? So the word, if your vocabulary has a size 10,000, then this word I is at 4343 index, want is at 9665. Similarly, a glass of orange. And your task here is to predict the last word. Now you want to build a language model so that we can predict the next word, and we will use the very simple neural network wherein we will feed uh, these words as input to the neural network, and these are the one hot encodings. O represents the one hot encodings, and E represents the embedding matrix. So dot product of O with E will give you the word embedding corresponding to that particular word, and then this is then passed through like this is then you perform linear combination and then non-linear activation to have a softmax layer of size 10,000. So and whatever whatever word will have the highest probability in the softmax, that will represent your last word. So that's how we generate this the training example, and we get the ej by np dot e comma o. So you make a dot product between e and o, and you get this small e, which is the word embedding. And this neural network layer has parameters w1 and b1, while the softmax has parameters w2 and v2. So here this layer has got the parameters w1 and b1, and this softmax layer has got parameters w2 and b2. And in this case, so the input dimension is 300 by 6. So if you remember last time we were talking about this, so we have, instead of having a 10,000 vector long one hot encoding, we have just 300. We assume that the words have 300 features. So the it's a 300 dimensional word embedding. So after doing the dot product of O and E, you will get a size of the vector as 300. So you have 6 inputs. I want a glass of orange, and and if you're so this is your window size, it's 6, and we are trying to optimize the E matrix. So we are trying to learn these weights, E weights, or what are the word embeddings in E, and we need to maximize the likelihood to predict the next word given the context. So the context is the previous words. So all these previous words are context, and in the context of the previous words, you are trying to predict the next word. And this model was built in 2003 and tends to work. So it works decently to learn. word embeddings. And so in this last example, we have taken a window of 6 words that fall behind the word we want to predict. There are other choices when we are trying to learn word embeddings. Suppose we have an example. I want a glass of orange juice to go with along with my cereal. Now to learn juice, the choices of context are, so if you are think about this, how you would try to predict that the, like, if this word juice is not given, how you would try to guess what should come there. So you will guess using some kind of context, and the context is last 4 words. So we use a window of last 4 words. So 4 is a hyperparameter, a glass of orange, and try to predict the next word next word from it. Now 4 words on the left, and 4 words on the right, and on the right. So a glass of orange on the left to go along with on the right. Then last one word or nearby one word. So glass word is this word glass is near orange. Is glass word is near juice. So this is the idea of skip grams model. So in NLP, if you use one word, then it's a unigram. It's these words are also, you can think of them as, so the in the terminology, if you are using two, then it's a 2 gram. N gram basically means you have n words. So the idea is so yeah, they say it's simple, and we'll talk in the next section. And researchers have found that if you want to build a language model, it is natural to use the last few words as context. So the last few words are a good context of the following word. But if your main goal is to learn the word embedding, then you can use all of the other contexts. So the all the other contexts can be the 4 words prior, 4 words ahead, last one word, or nearby, any word which is nearby to the word you are trying to predict. And so you can use, for word embeddings, you can use all the other contexts, and they will result in very meaningful word embeddings. So to summarize, the language modeling poses a machine learning problem where you input the context and predict some kind of targeted words, and posing that problem allows you to learn good word embeddings. Now, when we started, we talked about these two algorithms, word to wake and glove. So, word to wake, before word to wake, should understand what are skip grams. So, for example, we have the sentence, I want a glass of orange juice to go along with my cereal. So, we will choose the context and the target. So, the target is chosen randomly. So, let's say the target word is juice. So for target word as juice, orange can be a good context. So the distance between orange and juice in this sentence is just one step. It's just one step ahead. So how far? It says +1. Now orange and glass. So glass of orange, right? So if you pick the word glass as a target, so orange can be a context word. And so how far, like, is orange from glass? So it is in this direction. If you see, like, in the forward direction, so it is -2. So off is at -1 and orange is at -2. And I want a glass of orange to go along with my cereal. So for the word my, as target my, if you use the word orange as context, so your distance would be +1 +2 3 4, 1 2 3 4 5 6. So this is 6 steps ahead of the word orange. So now you can see that we have converted this problem into a supervised learning problem. And however, it's not easy, because so learning plus or minus 10 words forward or backward is not an easy task, and we want to learn this to get our word embeddings prop model. So now we will talk about this word to vec model. So for example, you consider that your vocabulary has a size of 10,000 words, and let's say your context word is C. So for example here, these are your context words, and your target word is T. So you are feeding in the context word into the neural network, and you are getting the target. Now you are framing the problem as you want to learn C to map to T, and you get the embedding of C by the making a dot product between the embedding metrics and the one hot encoding of C. And then you can use a softmax layer to get the probability of the target conditional to C. So you would get what your model will predict is y hat. And then the loss function that you can use is cross entropy loss. So this is a classification problem. You can use this cross entropy loss, and this model is known as the skip, also known as the skip grams model. So this whole process, it's also known as the word to vec model, or it's the skip grams model. And the last model has a problem with, so the softmax layer. So we have already discussed this before. Softmax is nothing but you take e to the power of, so if you have let's say 10,000 nodes, or in the last layer, so you would take e to the power of every node, and then you would basically compute a sum of that, and then you would divide that sum with each of the e to the power of x. So that would give you the probability of target conditional to the context. Now here we are summing 10,000 numbers, which correspond to number of words in our vocabulary. And if the number is large, so the computation can become slow. And one of the solution is that you can use a hierarchical softmax classifier, which also works as a tree classifier. So you can, rather than using just a single softmax layer or a softmax classifier, you can use this hierarchical softmax classifier. And in practice, the hierarchical softmax classifier doesn't use a balanced tree like the one which is drawn, and common words are at the top and less common words are at the bottom. So how to sample the context? See how to know which words are your context for your for the target words. And one way is to choose the context by random from the corpus. So you can randomly choose the context. So you would basically have some target words, and for those target words, now we are talking about choosing the context words. And if you have done it that way, there will be a lot of frequent words like the, of, to, that can dominate the words like orange, apple, durian, because these words which come most often, they would be so many in number. And so in practice, we don't take the context uniformly random, and instead there are some heuristics to balance the common words and the non-common words. So word to vec paper, it includes two ideas of learning word embeddings. One is the skip gram model. So we have seen the skip gram model, wherein you take the context words, map them to the target, you get the embedding, and then you have the softmax layer. And another is known as the continuous bag of words. So there is another way in which you can choose the context and the target, that is known as negative sampling. So it is allows you to do something similar to the skip gram model, but with a much more efficient learning algorithm. So for the context orange, if your target is king, then like you can also say that it's a negative, it's a negative sample. So that's the you can label it as 0, and juice you label it as 1. So given this sample that we have, so To generate a negative example, we pick a word randomly from the vocabulary, and notice that we got the word off as a negative example, though although it appeared in the same sentence. So although this word off has appeared here and it is near to this word orange, but still it is considered as a negative sample, because it's not a good sample, or it will not give you any idea of so if I just give you like this word off, you cannot tell what will come after that. So that's not a like it's so that is why it is a negative sample. Now the steps to generate the samples are: pick a positive context and pick a negative context, pick k negative context from the dictionary. So k is recommended from 5 to 20 in smaller data sets, and for larger data sets it is -2 to 5. And we'll have a ratio of k negative examples to one positive one in the data we are collecting. So now let's define the model that will learn the supervised learning problem. Let's say the context words are C and the target words are T, and Y is the target. So Y is the actual number, or the which we are computing. And we can apply a simple logistic regression model. So this logistic regression model can be drawn like this: you have a word embedding of the context, and then you take a dot product with the embedding vector, embedding matrix. You get the embedding vector, and then you have these so many uh, outputs. So you have an output layer with so many neurons, in this case 10,000, because that's the size of our library. So we are like having 10,000 binary classification problems, and we can only train k plus 1 classifier of them in each iteration. So now to get the negative samples, we can sample according to empirical features in word corpus, which means according to how often different words appear. But the problem is that we have more frequent words like the, of. So the best way is to sample them according to some kind of equation which is recommended by the word2vec authors. So they use a function f of wi. So this is probability of word I. So raised to power 3 by 4 divided by summation of f of wj, summation j from 1 to 10,000. So they basically take a function of that, and they would typically reduce the weights of these more frequent words. Now that was about the word-to-vec algorithm. There is another algorithm known as GLOVE algorithm. It stands for Global Vectors for Word Representation, and this is like a simplest of the word embedding algorithms, not used as much as word-to-vec or skipgram model. But since it is simple, so it has got a lot of people who use this algorithm. And let us say we take our example, previous example. I want a glass of orange juice to go along with my cereal. Now we will choose a context and target from the choices we have mentioned in the above section. So you will have context and you will have some target. Then you will calculate for every pair xct. So number of times the target t appears in context of C. Now xct equal to xtc if we choose a window pair. So if you just choose a window pair that there is a context of window. So let's say 4 words before the target word or 4 words after the target word. So this xct will be equal to xtc, but they will not be equal if we choose the previous words. For example, so for the way previously we have chosen the context words, this xtc and xct won't be equal. So in glove they use a window, so which means that they are equal. And the model is defined in so the model is defined in such a way that you take a sigma over like twice you will sum over the number of words, that is 10,000, and this f of xij is the weighting term. So that so we have seen, like for the words which are not very common, you will weight them, and theta I ej plus. So you will compute this loss function, and so this loss function you will have to minimize, and so this fx is a weighting term which is used to for not giving too much attention to or too much weight to words like is, the, and, is, which occur many times, and also to give so we have a log zero problem which might occur as there are no pairs for the given target. So for some pairs there for some given, for some targets there might be no context, or for some context there might be no targets. So for that that this log zero problem will happen. So this weighting term, it helps in that. And so to conclude, now if for the first time you're trying the word embeddings, you should try and download a pre-trained model that has been made and actually works best. Now, if you have enough data, you can try to implement one of the available algorithms. And because these word embeddings are computationally expensive to train, most ML practitioners will load a pre-trained set of embeddings. And a final note that you can't guarantee that the axis used to represent the features will be well aligned with what might be easily human interpretable, like gender, royal, age. There are various applications. The first is sentiment classification, and as we have discussed, so these are the on in the X is our sentences, and the Y are our ratings. So one of the challenges is that you might not have huge label data set for it, but using word embeddings can help get rid of this. So you have basically trained your word embeddings on lots of data. So you don't, if your present application doesn't have a lot of training or label data set, you don't have to worry, because your word embeddings can handle your problem. And so the common data set varies from 10,000 to 100,000 words, and a simple sentiment classification model will be something like this. So the desert is excellent, and you have one hot encoding, you have the embedding vector, embedding matrix, and then you have the embedding vectors, and then you basically take some kind of average, and you go to a softmax layer which gives you a rating from 1 to 5. So the embedding matrix may have been trained on, let's say, 100 billion words. Number of features in the word embedding is 300, and we can use sum or average given all the words and then pass it to a softmax classifier. This makes the classifier work for short or long sequences. So one of the problems with the simple model is that it ignores the word order. For example, completely lacking in good taste, good service, and good ambience has the word good 3 times, but it's a negative review. So the model, it's easy to fool the model, or like the model can think that this is a good review, and a better model uses an RNN for solving this problem. So completely lacking in good, so it ends in at ambience. And so if you train this algorithm, so this is a many to one architecture, you end up, so if you train this algorithm, you end up with a pretty decent sentiment classification algorithm. And also it will generalize better even if words weren't in your data set. For example, you have the sentence completely absent of good taste, good service. So the word absent is not in your label training set. So for example, if in your in your uh, in your label training data set, if you don't have this word absent, but it is there in your in the data that on which you have to now test the model. So it's not, but if it was in your 1 billion or 100 billion word corpus used to train word embeddings, it might still get this right and generalize much better even to words that were in training set used to train the word embeddings. So if that word is not there in your label training set data set, but it was there in the word embeddings. Then he's saying that it will your model will generalize. And so now comes the concept of debiasing word embedding. So there might be a lot of biases due to the kind of training that you would provide to your model, and you want to make sure that your word embeddings are free from undesirable forms of bias such as gender bias, ethnicity bias, and so on. So some of the analogies, for example, man is to computer programmer. Now, if you ask your model, woman is to, so if it gives homemaker, that's a gender bias. And for example, father is to doctor as mother is to, and if the model gives nurse, that's also a gender bias because mother can also be a doctor and a woman can also be a computer programmer. So why this might happen is because man as a computer programmer might be coming many times in the data set on which we have trained our word embeddings, and there is a gender bias in our word embeddings. So word embeddings can reflect gender, ethnicity, age, sexual orientation, and other biases of text used to train the model. And so the learning algorithms by general are making important decisions, and so if you deploy this model somewhere, and it should not be biased. And so Andrew thinks we actually have better ideas for quickly reducing bias in AI than for quickly reducing bias in the human race. So I mean, that's a opinion, and there are various ideas for addressing these kind of bias. And so the steps, this the steps can be, so you identify the direction. So calculate the difference between he and she, male and female, and choose some k differences and average them. So this will help you find this kind of a bias. And by that you have found out the bias which is a 1D vector, and the non-bias vector which is a 299D vector. So you would then neutralize the bias. So for every word that is not definitional, now the project is to get rid of the bias. So babysitter and doctor need to be gender neutral. So we project them on non-bias axis with the direction of bias. And so this doctor, you can see there is a there. So you on next. So this is a gender axis, and babysitter and doctor have a gender bias. And after that, they will be equal in terms of gender. So to do this, the authors of the paper train a classifier to tell the words that need to be neutralized or not. Now, you also have to maybe sometimes equalize the pairs. So we want each pair to have difference only in gender, like grandfather, grandmother, grandfather minus grandmother, he minus she, boy minus girl. We want to do this because distance between grandfather and babysitter is bigger than babysitter and grandmother. So then comes the sequence models and attention mechanisms. So you should be actually aware of these attention models. So we will maybe see the attention visualizations. Uh, yeah. So these are quite famous visualizations of the attention algorithm. And attention is used throughout these days in applications, in spatial applications, in sequential applications. We are working in time series data, natural language processing, computer vision. Anywhere you add attention, that the hope is that it will add value to your model. So we will see what basically is attention. So now sequence to sequence models are deep learning models that have achieved a lot of success in tasks like machine translation, text summarization, and image captioning. And Google Translate started using such a model. So this can be found on this Google blog, the this web page, Google web page. Such a model in production in late 2016. The models are explained in these two pioneering papers. And so J says that, however, understanding the model well enough to implement it requires unraveling a series of concepts that build on top of each other. And he thought that bunch of these ideas would be more accessible if expressed visually. So that's what he aims to do in this post, and you will need some understanding of deep learning, which we have already developed, I assume, from the past lectures. And I hope that it would be useful to reading the papers mentioned above. So to read these papers, this kind of understanding would help. And so a sequence to sequence model is a model that takes in a sequence of items, words, letters, features of images, anything, time series, and outputs a sequence, another sequence of items. So you can see this is a sequence to sequence model. You have this green input and you have the purple output. So you can have any length of as a sequence input, you can have any length as a sequence output. In a neural machine translation, a sequence is a series of words processed one after the other. So the output is likewise a series of words. So you can see that you are inputting French, and this neural machine translation model is outputting English. And so under the hood, the model is composed of an encoder and a decoder. So the encoder processes each item in the input sequence. So what it will basically do is you would first, and these words are not words, they are word embeddings now. So by now you should stop thinking of words as words, think of them as numbers. And so the encoder processes each item in the input sequence. It compiles the information, captures into a vector called context. And after processing the entire input sequence, the encoder sends the context over to the decoder. So which begins producing the output sequence item by item. So you see here this input is passed on to the encoder. Encoder generates a context. Context is passed on to the decoder, and decoder generates the output. So the same applies to the case of machine translation. Now, what is context? So context is a vector, or which is an array of numbers in the case of machine translation. The encoder and decoder tend to both be recurrent neural networks, and so you can check this recurrent neural networks. Will not go into that detail. We have already seen the recurrent neural networks. So it can be something like this: a vector. It can be a context vector, which is a vector of floats. So it's basically the number of hidden units in the encoder RNN, and these visualizations show a vector of size 4, but in real world application, context vector would be of size maybe 256 or 512 or 1024. Now, by design, an RNN takes two inputs at each time step: the input and a hidden state. The word, however, needs to be represented by a vector. So to transform a word into a vector, we turn to the class of methods called word embedding. So we have already seen what are word embeddings. So these turn words into vector spaces that capture a lot of meaning or semantic information of the words. For example, king minus man plus woman equal to queen. So these are the word embeddings for the French language. So French will have a different set of vocabulary. English will have its own set of vocabulary. Now that we have introduced our main vectors or tensors, so let's recap the mechanisms of an RNN and establish a visual language to describe these models. So recurrent neural network. So time step 1, RNN takes two input vectors, the hidden state at 0, and the input vector at 1. Now it processes them, and it then produces two output vectors, hidden state at 1 and the output vector at 1. So you can see that hidden state at 0 is passed into this RNN along with the input at 1, and it gives you the output at 1. So this is like you are inputting French, outputting English, or you are inputting a particular time series and you are outputting another time series. So the next RNN step takes the second input vector and hidden state number 1 to create the output of that time step. Later in the post, we'll use animation to describe the vectors inside a neural machine translation model. So in the following visualization, each pulse for the encoder or decoder is that RNN processing its inputs, generating an output for that time step. And since the encoder and decoder are both RNNs, each time step, one of the RNN does some processing. It updates its hidden state based on its inputs and the previous inputs it has seen. So let's look at this visualization. So J Sui Etudian. Now you see at time step number 1, J goes to the encoder. It gets the hidden state 1. Sui goes to then at time step 2, the Sui goes to encoder. It generates the hidden state 2. And now you can see at time 4, 5, 6, 7, these decoder is generating these outputs. So now you see first this hidden state 3 went in. Yeah. And so the decoder also maintains a hidden state that it passes from one time step to the other. So we just didn't visualize it in the graphic because we are concerned with the major parts of the model for now. Now let's look at another way to visualize a sequence to sequence model. So so we can see here. Now this J goes to encoder RNN, hidden state 1 is produced, then SUI goes, then student goes, and then it generates this hidden state number 3, which goes to the decoder, and then decoder also generates a hidden state and which goes to another decoder. So the context vector, it turned out to be a bottleneck for these models. Now it made it challenging for the models to deal with long sequences, and a solution was provided in these two papers. So these papers introduced and refined a technique known as attention, which highly improved the quality of machine translation system. So attention allows the models to focus on relevant parts of the input sequence as needed. That is a very uh, it's a very important statement. Now let's look at the attention models at this high level of abstraction. So an attention model differs from classic sequence to sequence model in two ways. First, the encoder passes a lot more data to the decoder. Instead of just passing the last hidden state of the encoding stage, the encoder passes all the hidden states to the decoder. So you can see that the encoder is passing hidden state 1, hidden state 2, hidden state 3 to the attention decoder. Second, an attention decoder does an extra step before producing its output. So in order to focus on parts of input that are relevant to this decoding time step, the decoder does the following. So look at the set of encoder hidden states it received. So each encoder hidden state is most associated with a certain word in the input sentence. So for example, J has passed through this encoder RNN. It produces this hidden state 1. Sui passes through the encoder RNN, produces another hidden state. Now, so he says that each encoder hidden state is most associated with a certain word in the input sequence. So given each hidden state a score, so you give each hidden state a score. So for example, you give these scores and multiply each hidden state by its softmax score. Now you compute these hidden state scores 13, 9, 9. Then you compute the softmax score. So you say You compute 13 plus 9 plus 9. It gives you, or you take e to the power of 13, e to the power of 9, e to the power of 9, compute the sum, and then you compute the softmax of the scores. So you get 0.96 probability or softmax value for this hidden state. This does amplifying the hidden states with high scores and then drowning out hidden states with low scores. So you can see this. Now multiply each vector by its softmax score. So you multiply each of these vectors with its softmax score. So you can see you are amplifying this first hidden state and suppressing the other hidden states. The scoring exercise is done at each time step on the decoder side as well. And so to bring this whole thing together in the following visualization, we'll look at how the attention process works. So the attention decoder RNN takes in the embedding of the end token and an initial decoder hidden state. So the RNN, it processes its input, producing an output. So you can see that first of all, this attention decoder RNN in the embedding of the end token. So end token is the end of the sentence, or end, the last, so the final or the ending of that sequence or the time series, and an initial decoder hidden state. So then the RNN processes its input, producing an output and a new hidden state vector. So which is known as H4, and the output is discarded. So in the attention step, you use the encoder hidden states and the H4 vector to calculate a context vector for this time step. So you have the encoder hidden states H1, H2, H3, which have already been weighted by these softmax scores. So you pass in, so the attention, you pass the last element to the attention decoder and an initial decoder hidden state, and the RNN, it processes its inputs, producing an output and a new hidden state vector. So the RNN you will pass in the hidden state, the previous RNN decoder RNN hidden state and the end, and this will basically generate a new hidden state H4, and it will also generate an output. The output is discarded. So in the next step, you can see, so you concatenate. Okay, yeah, so you see this, so we use the encoder hidden state and H4 vector to calculate a context vector C4 for this time step. So you concatenate this H4, and you concatenate this, you make this C4 by concatenating the encoder hidden state, this encoder hidden state and the H4. So then we pass this vector through a feed forward. So this one you pass through a feed forward neural network, and the output of the feed forward neural network indicates the output word of this time step. So repeat this for the next time steps. So you can see that you can repeat this for the further time steps to, like, go forward in time. And so there is another way you can look at this. So J sui tutient, and so you can see that each word has generated its own hidden state. So these are the hidden state 1, hidden state 2, and hidden state 3. These are for the encoder hidden states, and which are then passed on to the decoder. So in this model, it's saying is just isn't just mindless aligning the first word at the output with the first word from the input. It actually learned from training phase how to align words in a language pair. And an example, so you can visualize the attentions for the corresponding to the different words. And if you feel you're ready to learn, you can go to the sequence neural machine translation sequence to sequence tutorial. Why we are doing all this is because these are all directly applicable to time series problem. So you can just you can just say sequence to sequence time series forecasting, and then you can apply time series attention time series. So you can just go and check this kind of a sequence to sequence attention time series model and apply it to your weather or climate science dataset. So you have a time series as an input, you have a time series as a target. Okay. So then, yeah, these were some basics of attention. And then, yeah, we were talking about sequence to sequence architectures and attention. So I covered that some basic visualization of attention to give a background on attention models. And so we'll see some basics of sequence to sequence, that is many to many models, which are useful in various application using machine translation and speech recognition. And we'll start with this basic example of translating this sentence from French to this sentence in English. And our architecture will include an encoder and decoder. So encoder is RNN, LSTM, or GRU, and it takes the input sequence, the outputs the vector, which should represent the whole input. And so after that, the decoder network, also an RNN, takes the sequence built by the encoder and outputs a new sequence. So you have this A naught, which is a hidden state at 0 to the encoder, and this x1 to xtx. So tx is the length of the input, which is French in this case. So this is the encoder part, and then this goes to the decoder. Now decoder outputs the first word in the target, and then which also goes as an input to the time step 2 of the decoder, and which also takes the hidden or latent representation from the time step 1 of the decoder to predict what would be the second word. So Jane is visiting Africa in September, and the ideas are taken from these two papers. So we have already seen these two papers in that attention, when we were discussing attention. And an architecture similar to the mentioned above works for image captioning problem also. So in this problem, your input data is an image, and your output is a sequence. So y is a sentence. So the architecture uses a pre-trained CNN as an encoder for an image, and the decoder is an RNN. So you have an input CNN as an input, the decoder is an RNN, and so these are the papers which discuss about that. And there are some similarities between the language model we have learned before and the machine translation model that we have discussed. Machine translation is basically translating from one language to the other using machines, and but there are some differences. For example, in the language model we have learned is very similar to the decoder part of the machine translation. So in the language model, you have a context and you have a target word. So you have, like, you can do different things. You can build context and you can make the label data set. Whereas in machine translation, you have an input sequence and you have an output sequence. And so the problem formulations are slightly different. In language model, you have the probability of y1 comma y2 comma, so what you have to find out that kind of a probability, whereas in machine translation you have to find out the probability of the entire sequence y, which is a target sequence given an input sequence. So what we don't want in machine translation model is not to sample the output at random, and this may provide some choices as an input. So sometimes you may sample a bad output. For example, Jane visited l'Afrique en septembre. Yeah, I think that's how you have to say that. And why maybe Jane is visiting Africa in September. And so we need to give the best output as it can be. So you give this input X and you have to give the best possible output. and the most common algorithm is the beam search. So these can be three different output, and the beam search is the most common algorithm to find out the best possible candidate. So beam search is most widely used algorithm to get the best output sequence. It's a heuristic search algorithm. To illustrate the algorithm, we will stick with the example from the previous section. So we need y is equal to Jane is visiting Africa in September. Now the algorithm has a hyperparameter b, which is the beam width. Let us take the beam width equal to 3, which means algorithm will get 3 outputs at a time. So you input something, algorithm will give you 3 outputs at a time. So for the first step, you will get in, Jane, and September. So these are the 3 outputs that the model has given. Then for each word in the first output, get B next words. So for each word in the next output, you get B next word. So at least 3 next words. B next second words, and select the top B combinations uh, where the best are those that give the highest value of multiplying both the probabilities. So you have to find out probability of y1 given x and probability of y2 given x and y1. So in this we will then have in September. So you are basically also finding out the next word using beam search. Jane visit. So now if you notice this, you have discarded September as the first word. So there is a high probability of Jane being the first word, but the probability of September being the first word is discarded. And you repeat the same process and get the B best words for September is visit and so on. And in this example, keep only B instances of your network. So if B is equal to 1, your algorithm will become greedy search. So there are some refinements you can do to beam search. Let's not go into the details. And then there is something known as blue score. So blue score is how would you assess you will analyze the error of two sequences. For example, if that is those two sequences are from natural language. So the intuition is that as long as machine generated translation is pretty close to any of the references provided by humans, it will get a high blue score. So now suppose that the machine outputs, so if you have this as an input in French and you are outputting these two, so this is human reference 1, this is human translation 1, this is human translation 2, and let's say your model is outputting this sequence, the. So one way to evaluate the output, machine output, is to look at each word in the output and check if it is in the references. This is called as precision. So in this case, the appears in our target. So it will be 7 by 7 because the appears in y1 or y2. Precision is very high. So this, you can see this translation is very bad. So this is not a useful measure. And we can use a modified precision in which we are looking for the reference with the maximum number of a particular word and set the maximum appearing of this word to this number. So modified precision equal to 2 by 7 because the max is 2. So you won't count like that word, the maximum number of times that you would count that it would appear in a particular target is like you can set that max number. So we clip the 7 times by the max, which is 2, and here we are looking at one word at a time, so which is called unigrams. You may also look at n-grams, so bigrams and trigrams, n-grams. So if you are looking at 2 words at a time, so for example, the cat on the, that is bigram, and you can have an n-gram also. So you will compute a combined blue score for for an n-gram metric, and then Andrew provides some kind of attention model intuition, and he says that so far we are using sequence to sequence model with an encoder or decoder and decoder. So there is a technique called attention which makes these models even better. And attention has been one of the most influential ideas in deep learning. So the problem of long sequences that you have, so this is a long sequence. If you give this as an input and ask the model to output this English translation, so the encoder, for doing that, encoder should memorize this long sequence into one vector, and decoder has to process this vector to generate the translation. It's a very difficult task. And if a human would translate this sentence, he or she wouldn't read the whole sentence and memorize it, and then they try to translate it. So human would also try to translate it part by part, and same problem the machine will face. So the performance of this model decreases if the sentence is long. So you can see on y-axis is the blue score, on x-axis is the length of the sentence. And in this section, we will give some intuitions about attention model, and in the next section, yes, we'll discuss it. So at first, attention model was developed for machine translation, but it is used these days in computer vision and new architectures such as neural Turing machine. And attention model was described in this paper, neural machine translation by jointly learning to align and translate. Now for intuition, so Jane, so this is your French input, and suppose your model is a bidirectional RNN. So we have already discussed what are bidirectional LSTMs. So you have the flow in both the directions, because the context can be even the words which come later on in the sequence, and we give the French sentence to the encoder, and it should generate a vector that represents the inputs. So now to generate the first word in English, which is Jane, we will make another RNN, which is the decoder. And attention weights are used to specify which words are needed to generate a particular word. So to generate Jane, we will look at Jane visit l'Afrique. And in the attention model, yeah, we have already seen you will compute the attention. Basically you will compute, first of all you will pass all the encoder inputs to the decoder, and you will also compute how important a word is. So you will that is basically you will give attention to some words and more attention to some words and less attention to some other places in the sequence. And this can be used for speech recognition or trigger word detection. So for example, Alexa or Siri, you say Alexa start, so it just like it identifies the word Alexa as a trigger word. So you basically, that the model that is trained has given high attention or gives high weights to the word Alexa. And yeah, that's all for the sequence models. And so we will do some hands-on in the next class. I think this is already too much for today's session. And